objects moving around us. For instance, vehicles, transports, trucks, and bikes proceeding onward the street, planes flying in air, and ships cruising on the ocean, leaves tumbling from the trees, and water streaming in the waterway. Every one of these objects are changing their situation with time. At the point when an object changes its situation with time, it is supposed to be in motion. In these examples, motion is effectively noticeable to us. In any case, at times, movement is not effectively obvious to us. For instance, air moves all through our lungs and blood streams in our body. The moon moves around the earth, while the two together go around the sun. The sun itself, with its planets, goes around through our own cosmic system. Just in view of the activity, kinematics refers to us as the study of motion without considering its causes. Any motion where objects or particles take a straight way is viewed as the rectilinear motion. It is likewise regularly alluded to as straight motion or rectilinear kinematics. Regardless of whether it is essentially a young lady strolling straight down a way and a vehicle or car driving along a straight street, particles noticeable all around moving in a straight, equal line, or even the walking of military staff in an orderly fashion, every one of these practices is viewed as rectilinear movement. There are some true applications and examples that relate to rectilinear motion. In this lesson, you will learn how to describe motion. For this, we will develop the concepts of displacement, velocity, and acceleration. You will also learn how these quantities are related to each other. For an object moving along a straight line with uniform acceleration, we will obtain simple equations known as equations of motion, connecting these quantities with time. The location of an object with respect to a reference point or origin is called position.
For example, from the reference point O, the position of the particle at B is 3 meters. And from the reference point O, the position of the particle at A is -4 meters.
The displacement of a particle moving on a straight line is the change in its position. The straight line distance between an object's initial and final position with direction toward the final position. In symbols, delta x is equal to x minus x sub 0.
For example, if a particle moves from point O to point B, its displacement is 3 meters. If a particle moves from point O to point A, its displacement is -4 meters. If a particle moves from point A to point B, its displacement is 7 meters. And if a particle moves from point B to point A, its displacement is -7 meters.
The distance is the actual distance traveled. It is the total length of path taken by an object in moving from its initial to final position. Distances are always positive or zero.
For example, starting from the church, a procession has to take the following route: 50 meters north, 40 meters east, and 60 meters north. To go back, it must follow the same route but in opposite direction. What is the total distance traveled? To solve this problem, total distance traveled is the sum of the first 3 routes plus the sum of the opposite direction but the same route. We have the 50 meters plus 40 meters plus 60 meters plus the 50 meters plus 40 meters plus 60 meters is equal to 300 meters. For our next example, for his early morning exercise, Andy jogged 12 times around a circular tract of radius 5 meters. Find his total distance traveled and his displacement. To solve this problem, we have the distance, which is equal to the circumference of the tract. We have circumference is equal to 2 pi r, where r is equal to 5 meters. Substituting the values, we have circumference is equal to 2 pi times 5 meters, which is approximately equal to 31 and 416,000 of a meter. To solve the distance traveled, we have distance, which is multiplied by 12 times. So we have distance is equal to 31 and 416,000 of a meter times 12 is equal to 376 and 9900 of a meter. While the total displacement is equal to 0 meters since Andy went back to his original position.
The terms speed and velocity are used interchangeably in everyday situations. However, in physics, they have distinct meanings. The rate of change of the position of a particle with respect to time is called the velocity of the particle. Velocity is a vector quantity with magnitude and direction. The speed of a particle is the magnitude of its velocity. It is the distance traveled by a body in each time. The SI unit for speed and velocity is meter per second, or m over s. Speed is a useful idea because it indicates how fast an object is moving. However, speed does not reveal anything about the direction of the motion. To describe both how fast an object moves and the direction of its motion, we need the vector concept of velocity.
Velocity, the time rate of change of position. It is the displacement of a body in a specified time interval. Next, we have the average velocity, displacement divided by the total time elapsed. In symbols, we have v is equals to x minus x initial all over t minus t initial, or that is equal to delta x all over delta t. And since the value of our initial position and initial times are equal to 0, therefore we have v is equal to x over t. Next, we have instantaneous velocity, the velocity at a specific instant of time. In symbols, we have v sub instantaneous is equal to the limit of delta x all over delta t as delta t approaches 0, that is equal to the derivative of x in terms of time.
For our first example, Lian and Mikey, who are 150 meters apart, start walking toward each other at 3 meters per second and 5 meters per second respectively. How long will it take for them to meet? Find the corresponding distance traveled by each. To solve this problem, first, we'll let t be the time until they meet. And since distance x is equal to velocity v times t, or time, Leon walks 3 meters per second times t, and Mikey walks 5 meters per second times t. The sum of the distances they traveled is 150 meters. We have 3 meters per second times time plus 5 meters per second times time is equal to 150 meters. Adding two terms on the left side, we obtained 8 meters per second times time is equal to 150 meters. And to obtain t, we have 150 meters over 8 meters per second is equal to 18 and 7500 of a second. The second question seeks to solve the corresponding distance traveled by Lian and Mikey. Now we have the distance traveled by Lian is equal to velocity of Lian times time. Substituting the values, we have 3 meters per second times the obtained value of time, which is 18 and 7500 of a second, which yields to 56 and 2500 of a meter. While the distance traveled by Mikey is equal to velocity of Mikey times time, and substituting the values, we have 5 meters per second times 18 and 7500 of a second, which is equal to 93 and 7500 of a meter. For our next example, Boston Red Sox pitcher Roger Clemens could routinely throw a fastball at a horizontal speed of 160 kilometers per hour. How long did the ball take to reach home plate 18 and 4/10 meter away? To solve this problem, we are given the average velocity of the ball's motion in a particular displacement, namely change in x, which is equal to 18 and 4/10 of a meter. Equation 2.1 gives us v is equal to x over t. Manipulating, t is now x over v. But before using it, it might be convenient to change the units of v. We now have v is equal to 160 km per hour times 1000 meter per 1 kilometer times 1 hour per 3600 seconds is equal to 44 and 4400 meter per second. And to solve for t, we use the manipulated formula t, which is equal to x over v, which is now equal to 18 and 4/10 of a meter over 44 and 4400 meter per second, which yields to 414,000 of a second. Thus, the ball takes 414,000 of a second to reach the home plate.
To describe how the velocity of an object changes during a given time interval, we now introduce the new idea of acceleration. This idea depends on two concepts that we have previously encountered: velocity and time. Specifically, the notion of acceleration emerges when the change in the velocity is combined with time during which the change occurs. In everyday conversation, to accelerate means to speed up. The accelerator in a car can in fact cause it to speed up. The greater the acceleration, the greater the change in velocity over a given time. The formal definition of acceleration is consistent with these notions, but more inclusive.
Average acceleration, the rate of change of velocity or the change in velocity per unit time. In symbols, we have A is equal to delta V all over delta T, that is equal to V minus V initial all over T. Next, we have instantaneous acceleration, the limit of the average acceleration when the interval of time considered approaches zero. In symbols, we have A sub instantaneous is equal to the limit of delta V all over delta T as delta T approaches zero, that is equal to the derivatives of V in terms of T. Next, we have average velocity, object with constant acceleration, that is equal to average velocity is equal to V plus V initial all over 2.
For example, the position of an object as a function of time t is given by x, which is equal to the quantity of 3 and 5/10 meters over s cubed times t cubed minus 2 meters per second times t plus 5 meters. Give the velocity and acceleration as a function of time, and find the velocity and acceleration at time, which is equal to 2 seconds. To solve this problem, take note that the velocity is the first derivative of position with respect to time, and acceleration is the first derivative of velocity with respect to time, or the second derivative of position with respect to time. Now, velocity will be equal to the derivative of x in terms of t. Substituting the value, we have the derivative of 3.5 meter per second cube times t cube minus 2 meters per second t plus 5 meters in terms of time. Get the derivative of x with respect to time. Given the position as a function of time, apply the rule of differentiation. H of x is equal to f of x plus minus g of x. Then h prime of x is equal to f prime of x plus minus g prime of x. Get the derivative of 3 and 5/10 meter per second cube times t cube and 2 meter per second times t with respect to time. Take note that the derivative of a constant is 0. Now we have v, which is equal to 3 times 3 and 5/10 meter per second cube times t raised to 3 minus 1 minus 1 times 2 meters per second times t raised to 1 minus 1 plus 0. Simplifying the term, we obtained 10 and 5/10 meter per second cube times t squared minus 2 meter per second. To determine the acceleration, we now use a, which is equal to the derivative of v or velocity in terms of t or time. Substituting the equation obtained from velocity, we now have acceleration, which is equal to the derivative of 10 and 5/10 meter per s cubed times t squared minus 2 meters per second in terms of t. Get the derivative of 10 and 5/10 meter per second cubed times t squared with respect to time. Take note that the derivative of a constant is 0. Now we have acceleration, which is equal to 2 times 10 and 5/10 meter per s cubed times t raised to 2 minus 1 minus 0. And in simplifying the equation, we have 21 meter per second cubed times t. To determine the velocity and acceleration at t, which is equal to 2 seconds, we substitute t, which is equal to 2 seconds, from the obtained equation of the velocity and acceleration. We now have velocity, which is equal to 10 and 5/10 meter per second cubed times 2 seconds squared minus 2 meters per second. And that yields to 40 meters per second. And for the acceleration, we have 21 meter per second cubed times 2 seconds, which is equal to 42 meters per second squared. For another example, the head of a rattlesnake can accelerate 50 meters per second squared in striking a victim. If a car could do as well, how long would it take to reach a speed of 100 km per hour from rest? First, convert the car's final speed to International System of Units to make it easier to work with. We have 100 km per hour times 1000 meter per 1 kilometer times 1 hour per 3600 seconds, which yields to 27 and 7800 meter per second. The acceleration of the car is 50 meters per second squared, and it starts from rest, which means that the initial velocity is equal to 0. As we have found, the final velocity v of the car is 27 and 7800 meter per second. Manipulating equation 2.2, let us solve for time t. Acceleration, which is equal to final velocity minus initial velocity over time. And now, t is equal to final velocity minus initial velocity over acceleration. Substituting, we find time, which is equal to 27 and 7800 meter per second minus 0 meter per second over 50 meters per second squared, and that yields to 5600 second. If a car had such a large acceleration, it would take 5600 of a second to attain the given speed.
Thank you very much for watching. We hope that you learned. See you on our next topic. Bye!